So now, how do we know that the Schrodinger equation is making predictions that agree with our observations? Well, we got to do an experiment. And the experiment we're going to do is we're going to take a glass tube like this. Right? We're going to pump it out, and we're going to fill it with hydrogen, H2. Okay? And then in this glass tube, there are two electrodes, a positive electrode and a negative electrode. And what I'm going to do here is that I'm going to crank up the potential difference between these positive and negative electrodes higher, higher, higher until at a point we're going to have the gas break down. A discharge is going to be ignited, just like I'm going to do over here. All right, did I ignite a discharge? Yep, there it is. And the gas is going to glow. We're going to have a plasma formed here. And what we're going to do is we're going to, and what happens in this plasma is that the H2 is broken down into hydrogen atoms. All right? And these hydrogen atoms are going to emit radiation. That's some of the radiation that you're seeing here in this particular discharge lamp. We're going to take that radiation and we're going to disperse it. That is, we're going to send the light through a diffraction grating. This is kind of like the two-slit experiment. And when you look at it, you're going to see constructive and destructive interference. But when you look at the bright spots of constructive interference, you're going to find that those bright spots now are broken down into different colors, purple, blue, green, etc. And that's because the different wavelengths of light have different, the different colors of light have different wavelengths. And if they have different wavelengths, well, then the points in space of maximum constructive interference are going to be a little different. And so we're going to literally separate the light out in space depending on their colors. And we're going to see what colors come out of this. Okay? And so now in order to help you do that, we've got some diffraction grating glasses for you. You should put them on and look into this light. And you will be able to see off to your left and to the right some very distinct lines. Okay? And if you look into the lights above, you can see all different colors in the white light. All right. Do you see the hydrogen lamp? I know that the white lights above the room are more interesting because there's a real whole rainbow there. All right? Oh, yeah. Okay, I'm going to turn the lamp a little bit since not all of you, if you're way on the side, can see it. All right, so I'm going to start over here. I'm going to turn the lamp a bit. All right. Can you see that now? All right, you should see a bunch of lines here to your left and some to your right. And then, of course, you'll see some up here. But they'll probably be dispersed best to your left and to your right. Pardon? Can we dim the bay lights? Can we dim those big lights over there? Probably not. All right. Okay, I'm going to turn it over here. Can you see it? The spectrum that you should see is what I'm showing on the center board there. All right, you see it? Pardon? You have to look at the light. Oh, thank you. Hey. Thank you very much. Can you see that better? Yeah. Okay, I'll turn it back there. All right. You see the emission spectrum now? It's a little better, huh? Okay. So let's see if we can try to understand this emission spectrum that you're seeing. What you should see, the brightest, what you should see is a purple line. No? Well, let's see. The purple line is actually rather weak, I have to say. If you come really close, you can see it. And you're invited to come up a little bit closer. The purple line's kind of weak. All right, so the purple line is kind of weak, but the blue line is really strong, right? And then there's a green line, which is also a little bit weak. And I can see, because I'm really close, there's actually, well, I'm not going to tell you that. There's a green line there, and then there's this red line, all right?